So we're going to think about mass spec with a bromine, a molecule containing bromine. So I'm just putting R there to start off with, and we'll look at a specific example in a second. So the first thing that happens is that electron beam, right? He knocks one of the electrons from the bromine out from the lone pair. Right? So you always look for lone pairs. Think about the electrons. Where are the easiest electrons to knock out? So you want something that's not super electronegative, has a lone pair that you can knock one electron out. Notice single-headed arrow, because that means it's indicating one electron. A double-headed arrow means two electrons. So single-headed arrow, electron beam knocks that one electron out. That creates what we call a radical, so there's a plus charge, cation. A radical cation. Radical now because it's an unpaired electron, cation because we'd lost one of the electrons. So from this point, now we want to make stable carbocations. Right? Normally, if you have a bromine with a plus charge, that bromine is pretty unhappy, right? Does this bromine have a full octet anymore? Well, no, we just knocked an electron out. So a lot of times we'll just break this bond. Whatever R group is, we'll just, right, the simple thing to do is take these two electrons in a bond. Both those two electrons go to bromine. So what do we make? We make R. Now the R has a plus charge, wherever the R is. And the bromine, how many electrons does the bromine have surrounding it now? 7. How many valence electrons does bromine have? 7. So this bromine is neither charged, right? It's not charged, so it's neutral. Is there anything else? Do we balance? Does it have an overall plus charge? Do these two things have an overall plus charge? Yep, so we're good. So we have the radical cation became a cation and a radical. A cation and a radical. Right? And of course, our cations, if we think back to cations, we know we want to make really stable cations. So those go back to our carbocations rules, right? Rules of carbocations. How do we stabilize carbocations? Hyperconjugation, pi bond resonance, and lone pair resonance. And the best of those is lone pair resonance. Not because lone pair resonance is the best. Why is it the best? The reason why? Because usually with lone pair resonance, you end up having every atom has a full octet. Pi bond resonance, hyperconjugation doesn't do that. So it's not just, is it enough to just say lone pair resonance? No. You need to say lone pair resonance, which gives all the atoms full octets. So those that basic rule here. Now back to using those carbocation stabilization rules. Bromine doesn't have a plus charge because a bromine by itself has 7 electrons, 7 valence electrons here. So it's weird because people will think, well, this plus charge moved. Like plus charges don't move. What moves in organic chemistry? Only electrons move, right? So this plus charge here is like a placeholder because there's an electron gone. But once this bromine gets these 2 electrons, now it has 7, which is what it normally starts out with. It wants 8, right? But it starts out with 7. That's why we call it a radical because it has an unpaired electron. It's a radical in the cation. I would never say that these things are stable. I mean, a bromine radical is actually more stable than a chlorine radical. Well, why would that be? Bromine's bigger, right? Bromine can be more, right? It can be electron efficient because it's larger. It can help spread out that efficiency, right? Whereas chlorine couldn't. But are these things very stable? Oh no, these are reactive things, right? In mass spec, right? We're using an electron beam. We're breaking up a molecule. This is a high energy thing where we make a radical cation and then this molecule just starts falling apart, right? We talked about limbs being lopped off, methyls flying everywhere. Like the molecule just starts breaking down because it's so unstable and it's in such a high energy environment. Right, so we're gonna take a look at an example we have drawn, the group had drawn. So you have a bromine and a chlorine on a benzene ring and you're gonna put that in the electron beam. So what's gonna happen? What's the electron beam do? It's gonna knock out an electron. Which one is it gonna knock out? Why the bromine? It doesn't have to do with size. bromine or chlorine? So we're trying to knock out an electron. So what do you need to be thinking about if we're trying to lose an electron? The consensus we came to was knocking the electron out of the bromine. And the reason that was either size or electronegativity, but how we frame it is important. The bromine is larger. Therefore, its electrons are farther from the positively charged nucleus. So they're going to be easier to knock out because it's big, and also because the bromines, that in that case versus chlorine, is less electronegative because of its size. So these electrons are going to be easier to knock out. And so if you're just thinking about this, you're always going to go for the path of least resistance. So the easiest electron to knock out would be one from the bromine, doesn't matter which one. Oops, fishhook. Boom. Does that mean it'll never knock an electron out of the chlorine? No, that doesn't mean that. But the most likely thing to happen is going to knock an electron out of the bromine. And then it's the same process as before. But that, all this was, right, was an electronegativity size kind of question, but in a mass, but involving mass spec. So it's something you already know, but just use in a different context. Right? Don't forget to use your periodic tables. You have a bromine and chlorine. What's the difference between those two things? The size, bromine's bigger, and the electronegativity. So it must be something about that, right? It has to be something involving that principle. What exactly it is, that's what you need to explain. So don't just say size, don't just say electronegativity. Talk about how both of those things, those physical properties, affect this in a real way. And then from here, it's just the same thing as before. These two electrons go to the bromine. This is the radical cation. Then you make a radical and a cation. You go from there. So I'll continue on the mass spec train. If we're looking at Wkshp number 2 from this year, kind of the third question. What if we don't have lone pairs in a molecule? Then what do we do? Then you just think the whole molecule just loses an electron. So it's not really a way to draw that electron being knocked out. So you say, okay, the electron beam comes in, and it goes out of the molecule, then boom, knocks the electron out. I don't know where it's being knocked out at, but I know an electron got knocked out. So then we draw the molecule, put a little here, a dot plus, because that's a radical cation again. I don't know where the electron got knocked out. Got knocked out somewhere. So within the whole molecule, I lost an electron. That's all that's showing. Right? So it's the molecular ion. So it's no different than having a lone pair, but if you don't have a lone pair, you just say the electron got knocked out somewhere. So we got a dot plus, radical cation. And now at this point, the question said, where does the mass peak at 57 come from? What's the most likely thing to happen there? So the molecular ion, the mass of this, right, is 72, right? If you just, like this molecule right here, if you add up all the carbons and hydrogens, the mass is 72 grams per mole. If you take out one electron, does that change the mass very much? Right, remember like losing a tooth? Oh, that changed your mass very much? No. But the question is, okay, well this molecule is going to break up now. And the question was, there's a peak at 57. Right? Remember, you only see the positively charged fragments in mass spec. Or talk about that, the only positively charged fragments. Which fragment is most likely to be at 57? So if you start with 72, what's the difference between 72 and 57? A methyl group, a CH3. So then the question is, well, which CH3 should we lop off? Well, we want to lop off the one that gives us the most stable carbocation, right? Because we talked about having stable cations. So I'm going to number this. 1, 2, 3, 4, 5. We talked about this a little bit in class. We did when we talked about this in class. So we know we need to lose a CH3. The question now is, which CH3? So which bond do you want to break? 3? 3 and 2, or you could do 1 and 2, right? Because if you did net, these are the same peaks. These would be the same, right? So you do either one. So we'll do, let's say I'm going to break it off there. Now you don't need to show any arrows here, but you need to show two things, right? Just like before, we have a radical cation. So we need to make a cation and a radical. So which one of these should have the plus charge, carbon 2 or carbon 3? Well, you see a peak at 57. That means the peak at 57 is the plus charge fragment, right? You only see plus charge stuff. So where's the plus charge going to be on carbon 2 or carbon 3? Carbon 2, right? That's the cation. One, two, 4, 5. And then what's the radical piece going to be? Just a CH3 with a dot. And that's for carbon 3. Because now you have your cation and you have your radical. Why not break between 4 and 5? That loses a methyl too, right? Why not do that? That'd make a primary carbocation, which of course you know is not as stable as a secondary carbocation. Because this one has more hyperconjugation buddies than a primary would. Sorry, this is like a bracket. This is meant to be like a bracket. Like I'm bracketing in this whole molecule. The whole thing lost 1 electron. That's a bracket, sorry. So yeah, so you write this in as the whole molecule, right? I don't know where the electron left from, but the molecule lost an electron. So I'm saying the whole molecule lost an electron, so you put a dot plus. That's a radical cation. And then it breaks down into a cation and a radical. So very similar to the lone pair one, but something with lone pairs, you know exactly where that electron got knocked out. When there's no lone pairs, you don't know where it left. So the question is, well, wait a second. How the heck do I know? You start talking about methyl group way ahead of time. How do I know you lost a methyl group? So I'm looking for a peak at 57. I know the whole molecule, the molecular ion, is at 72. So all I do was 72 minus 57, 6, 1, that is a 5, 1, 15. When you see a 15 being lost, that should trigger methyl in your head. Why? Because carbon is generally 12 grams per mole, and each hydrogen's 1. So a CH3 has a 12 plus 3 ones, that's a 15 mass unit. Losing a methyl is 15. Losing an ethyl, a CH2, CH3 is 29. Right? So you can start to see those pieces that get cut off. So that's how I knew I was going to lose a methyl as a radical piece, because I subtracted here. All right, so let's take a look at an IR question from question number 5 from this year's number 4 quiz, 2017. The question states, would you expect the carbon-sulfur double bond stretch in the molecule below to be higher or lower than a ketone C-O stretch? Explain your reasoning. So this was a poorly worded question. What we end up diverging is actually kind of interesting. We can cover 2 different principles here. What I meant to say when I said higher or lower, I wanted to mean higher or lower frequency. So with a sulfur versus an oxygen, this C double bond S stretch have a higher or lower frequency in the IR than the ketone. So what's the difference between a sulfur and an oxygen? The mass, the size. So if something's heavier, are you going to be able to stretch it at a higher frequency or lower frequency? The heavier things are going to go at a lower frequency. So I was looking for a lower frequency, right, based on the mass of sulfur. That's what I was looking for. That's what I was trying to ask. But I forgot this word, frequency. So the other side of the coin, what most of you guys heard or read, when I said higher or lower, you thought I meant intensity. Right? How far down in an IR does the stretch go? Does it go there, or does it only go to here? You thought I meant intensity. And intensity is based on the polarity. So if that was the question, then which one is going to have a more polar bond? Oxygen to carbon or sulfur to carbon? Which one's more electronegative, oxygen or sulfur? Oxygen. So the more polar bond is going to be this one. So I would have a more intense stretch, right, in the IR. So the question actually ended up being okay because we had to interpret it 2 different ways, but just want to make sure we understand 2 different principles. The frequency changes based on the mass right? The reduced mass, or the length, right? The length of the bond can change, right? The force constant, or the force constant, the reduced mass, that's Hooke's law. But the intensity, how far down the IRP goes, is all about the polarity. Right? So this would be the more polar bond, and this would go at a lower frequency because of the mass. So here we're doing workshop number 6, problem number 3. First thing you need to do, C10H12O, gotta calculate the degrees on saturation. Gotta get that right. Gotta. That case, in this case, it's 5. Anything more than 4, we think, ding, 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 benzene ring. Right, so we're thinking this. Right? We're not sure yet, we're thinking that. So now let's look at the IR piece. What are some of the frequencies you get in the IR? 30, 28, 29, 26, 17, 17. What do we think about 30, 28? Alkene CH. So I would say sp2CH. Same difference. About 29, 26. sp3CH. 17, 17. Carbonyl group. We could say, so I always get cautious about, right, because we don't know what resonance is going on or what else is going on. Right, you could be bold and say it's a lot. I know it's a ketone, but it's not right now. We don't have to. Let's just say we know it's aceto-bondo. Right, we know it's one of these. That's good because that covers, of course, one of our degrees on saturation too, right? Degrees on saturation, of course, meaning number of pi bonds plus the number of rings, right? Total. That's pretty reasonable. Just something to think about. If it's an OH, I'll say broad. I'll give a range and say it's an OH, right? They'll basically say it's an OH, right? Be careful for that. Okay, that's what that told us. Let's look at the NMR. So at NMR, we have 4 peaks, or 4 apparent peaks. So I'm going to label these A, B, C, and D. Always like looking for those aromatic peaks first, because that can give you an idea about the substitution of the benzene ring. So in this case, they're given a range here, and they're saying multiplet with 5 hydrogens. So what is that telling you? What kind of benzene ring do we have? These are all aromatic. This is the aromatic region, right? What kind of benzene ring do we have? How many hydrogens are in the aromatic region? 5. So how many substituents are off the benzene ring? Just 1. So it's a mono-substituted benzene ring. That's what this tells us. We don't know, right? So they're all kind of overlapping each other, the peaks. So that comes back to this, but we can subtract out, this A tells us a piece though, right? It tells us one of our pieces. It tells us we have a benzene ring, and it's only substituted at one spot. But do we know what's on the benzene ring yet? Nope, squiggly line, but we know this. So we can subtract out that piece from our formula. So how many carbons is that worth? C6, H5. So C4, H7 left. Oh, and the oxygen. Very good. Let's look at B. So, well, or we can let's look at, I mean, it doesn't matter the order we do these in. You can kind of pick and choose, but you can see CH and CH, and these are both triplets. This is a singlet. So what does this tell you about B and C? I didn't give a coupling constant here, but if they're both triplets, how many nearest neighbors do you have if you're a triplet? Triplet, you have 2. Do you think B and C are near each other? They have to be, right? So they're coupled to each other. So how do we draw that? Well, there's like a CH next to a CH. So one of these CHs, and we don't know what's on the other side here, right? Carbon has 4 bonds, no charged atoms. So let's just say this one can be B, and this one can be C. So that means is whatever's on the other side here has to be different, right? Do we know what's over there? Nope, don't know yet. But we know these two are different, and they're talking to each other because they're both triplets then. So let's subtract this piece out. So how many carbons is that worth? Minus C2H4. So end up with a C2, H3, and O. So what we've done, we've checked off that piece, that piece, that piece. What about D? D is 3 hydrogens. It's a singlet. It's a CH3, right? It must be a CH3. We're going to call that D. Don't know what's on the other side. That checks off that piece. So subtract CH3 minus CH3, C and an O. Well, that's easy. We already had that piece, right? That's over here. You know there's a carbonyl at some point. So that we can subtract out the C and O. So what are our pieces left? We have a methyl, we have a monosubstituted benzene ring, we have the carbonyl, and we have this CH2 piece. Now, let's go back and look at the frequencies and make sure they make sense where we put this together. Right? There's probably only one way to do this. Maybe. Yeah, there's only one way to do this. So let's take a second and see if you can put it together. All right, the answer for this is, so we have a benzene ring. With only one substituent. The substituent I'm going to put there is going to be one of my CH2s. Both my CH2s. The other side is going to be the ketone. Make sure this works. CH3, that's a singlet. CH2, that's a triplet, 2 nearest neighbors. CH2, that's a triplet, 2 nearest neighbors. And then a monosubstituted benzene ring, it all fits in. Be careful, one of the things that people would try to maybe do that would mess up is if they try to put this D next to C. Right, but that wouldn't work, right? So maybe let's draw it. So I'm gonna draw the wrong answer here. Let's draw the. Right, this could be an alternative answer. That would be wrong though, because this CH3 has how many nearest neighbors? 2, so that would be a triplet. Also, what frequency would this CH3 be at? 0.5 to 1.5, and we had a CH3 at 2.11, so that also wouldn't make sense. This CH2 would be a triplet of quartets, and what frequency would it come out at? Also 1.5 to 0.5, so that wouldn't make sense either. So double check, always double check, right? Double check. Do we cover our degrees on saturation? We had 5, so we had ring, 1, 2, 3, 4, so total there. Then 5, our 5th degree on saturation. We're good to go. There's our answer. So make sure you always check the N2. So looking at a question from workshop number 3, question number 2 from this semester. This is one of the ones where it said, give the splitting pattern, splitting for the protons in the molecule below. And then I had an example kind of showing how to do it. And so I had these labeled already as A, B, C, and D. So let's go through this. So I'm already telling you there's 4 different types of hydrogen. That's nice. So A is worth how many hydrogens? 3 hydrogens. How many nearest neighbors does A have? 1. So what kind of splitting will A have? Be a doublet. B is worth how many hydrogens? 1 hydrogen. How many nearest neighbors does B have? 3 and 2, 5 total, but 2 different neighbors, 2 different songs. So what's B gonna be? B, it's gonna be a triplet. It's gonna be a triplet from C of, and what's A gonna turn it into? Quartets. Does not matter, I'm not gonna care. Based on A. So a triplet of quartets. C, how many hydrogens is C worth? 2. How many nearest neighbors does C have? 1. So C is going to be split into a doublet because of B. A was split into a doublet because of B as well. And then D is worth how many hydrogens? 3. Any nearest neighbors? So it's going to be a singlet. Then the other question is which hydrogen is the most d-shielded? A, B, C, or D? Which one's going to be the most d-shielded? B. And where would it be at? So B is going to be the most d-shielded. So it's right next to that fluorine. Looking at your tables, it should be around, you know the range, but you should know the specifics one for this one. Where would this be at? What ppm? 4.5. Approximately. Right, remember that's the one with the nitrogen, oxygen, halogen? Nitrogen is like 2.5, oxygen is like 3.5, halogen is more like 4.5.
So fluorine shows D-shields hydrogen.
Yep, fluorine's sucking away electron density, which makes this D-shielded. It's going to get knocked down and going downfield. You don't have the electrons to shield it because fluorine's pulling all those electrons away. So it's going to get D-shielded downfield.